next speaker is Mindy Beerends. Mindy is currently the MIC at CWSU Indianapolis and getting ready to transition to the MIC in Grand Forks. Is that right, Mindy?
Yep, WFO Grand Forks in about a week and a half.
All right, and we hate to lose you here, but happy to see you moving up there. So, and she's going to talk to us about how upper air data used by the air traffic controllers for planning routes and airspace changes. So go ahead and take it away, Mindy.
All right, thank you. So yeah, my name is Mindy Beerends, and I'm the MIC at the CWSU in Indianapolis right now. I've been here about 2 years. For about the next week, I'll be here. So I'll look at the Center Weather Service units and how we use the observational data, specifically the upper air data in our aviation forecasting and our decision support for the air traffic control center. Just taking a little few minutes to also just introduce you to Center Weather Service units and what some of the services are that we provide, as not a lot of people are familiar with what all the CWSUs do. So a little history on us as well. There's 21 Center Weather Service units in the air traffic control centers. We've been in these traffic control centers since 1979. We have 16-hour daily operations, usually somewhere between the hours of 5 a.m. and 9 p.m., with 4 operational staff, meaning the MIC, and 3 forecasters. We do also have cross-trained forecasters from nearby WFOs. That's been a program to kind of help CWSUs remain staffing, especially in times of sickness or in times of vacancies. We provide decision support services for the entire airspace and underlying terminals. And some of our collaboration partners are the Aviation Weather Center, the FAA Command Center, WFOs, and of course our surrounding CWSUs. A little information about the National Airspace System, or the NAS, and traffic management. So the majority of the traffic planning is out of the FAA Command Center in conjunction with the traffic management units, which are inside the air traffic control centers. They participate in this air route traffic planning through national coordination calls that are held about 2 hours, every 2 hours every day. And they institute different traffic management initiatives, TMIs, or playbooks that are routing the traffic in different areas, specifically focusing on areas where we may have thunderstorms, areas where we have inclement weather, and focusing on the safety and efficiency of the air traffic. So picture to the right is just looking at some of what I call the jet highways across the United States. So that is some of the routes that the airspace is using to plan traffic across the United States. Also within the airspace, we have what's called sector stratification. So different airspaces are divided into sectors spatially, and then also along the altitude, different stratification along that altitude as well. So the majority of aircraft and commercial aircraft, when they're en route, flying between the levels of 18,000 feet and above, specifically a lot of times above 34,000 feet. Then we have different altitudes for different classes of aircraft. And then when you get down to below 15,000 feet to the surface, and especially near a terminal location, then we get into the traffic radar approach controller, the TRACON airspace. So if you were flying, say, from Chicago to DC, you would go through a number of different air traffic control centers. So first, when you take off, you're dealing with the Chicago Tower. Then you would go to the Chicago TRACON and deal with the controllers there. They would hand you off to the Chicago Air Traffic Control Center. And then as you're moving, you'd either move through the Cleveland or Indianapolis Air Traffic Control Center into the DC Air Traffic Control Center. Before, as you approach the DC terminal, then you would get the DC TRACON and then finally the DC Tower as you land. So that's kind of just a picture of how the air traffic controllers work throughout the airspace. Also looking at the services that the CWSU provide, we do scheduled briefings every day at our stand-ups at 7 a.m. and 3 p.m. We also provide on-demand and update briefings. We have 3 pre-duty weather briefings that are recorded daily at 5:45 a.m. by 1 p.m. and 9 p.m. We issue our warnings, which are called Center Weather Advisories, or CWA, so it's a little bit of a transition from WFO Life to CWSU Life with the CWA acronym. And then we also work on collaboration with convective forecasts, or the TCF collaboration. We provide aviation forecast products, or PIREP solicitation, so basically different conditions that meet when air traffic controllers should get pilot reports from different aircraft. We forecast for thunderstorm, turbulence, icing, ceilings and visibility below 5,000 feet and 5 miles, altimeters, and jet level winds. We do TAF collaboration, certain terminals across our airspace. We also look at a day 2 forecast with the FAA, and that's for traffic route planning as they move into maybe critical weather, large weather systems that might be impacting the area in day 2. And then specifically in Indy, we have a freighter operation forecast due to the large amount of UPS and FedEx freighter traffic out of Indy, Louisville, down in Stanford, Covington and Cincinnati, and then also the big FedEx hub in Memphis. So some of the ways we use the upper air observation data, one of them is to verify our pre-duty weather briefing wind levels and the forecasts and conditions that we're putting out. So at different times of day, we're forecasting the jet level winds around 300 millibars, the 10,000-foot winds, and the 3,000-foot winds. And this is to support the airspace, both the en route traffic, that TRACON traffic, and then down to the terminal locations. Another way those winds impact that are important for those forecasts is looking at the jet routes and the traffic management across the United States. So depending on where those winds are, especially the jet level winds and the high sector jet routes could determine how traffic is moving across Indianapolis on those different jet routes. We also have, if you look here, 5 different arrival routes into O'Hare across the northwestern portion of ZID. So some of that can be impacted as far as how that traffic flows along those routes as it's moving into arrival and departure at O'Hare. We also look at those winds, the impacts for the flying in the different jet streams, if they're flying in those magnitudes of the jet stream, especially those jet streaks. So they can be fuel savings. There was a Washington Post article that looked at a study where there can be a 16% reduction in fuel use and even 2.4% reduction in total CO2 emissions if the traffic planning was to use these jet streaks in the strong high magnitude areas of the jet stream for more of their traffic planning, especially in long routes, cross country and international routes. Some timing considerations brought up in this article too, especially like say a flight from LA to New York could be an hour early looking at eastbound. So some of their arrivals could be different if they're trying to take use of where the highest magnitudes of those jets are in place, especially along their routes as they encompass them. And then there could also be a 2 hours late if they're flying into a strong headwind as they're flying westbound, say from New York to LA. Another way these winds are used in impact aviation and why they're important for us to get them correctly in the forecast and looking at the conditions, so using those upper air observations, is looking at a type of traffic strategy called miles or minutes in trail. So the miles or minutes in trail is a required number of miles or minutes of separation needed between aircraft as they're flying a specific jet route or if they're flying over a certain area through a sector or certain places. So especially used for departures and arrivals and can provide space for merging or departing traffic. And so like right here where I was mentioning the area of the 5 arrival routes that are across the northwestern Indianapolis airspace that are going into O'Hare each morning. We have a morning push of traffic into O'Hare between around 6 a.m. to 9 a.m. Eastern time, in which all the traffic from much of DC, Atlanta, Charlotte, Memphis, areas to the south and southeastern airports are all heading towards Chicago and coming across and funneling across those jet routes into northwestern Indianapolis airspace. So depending on the impactful weather that's in that area and the winds that we are seeing could increase that number of miles or minutes in trail. So a lot of times maybe there might be 15 minutes in trail, but if we have special weather or high volume of air traffic, in order to get the planes in safely, they might push that up to like a 30-minute in trail or something like that. And that means that we have a 30-minute separation between aircraft and they need that longer time to get the aircraft in. So that can have impacts all the way back to, you know, other flights taking off because there's not enough room in the airspace for those jets to get up on those routes as we're waiting for other aircraft to land due to the separation that's needed. Another impact from the winds as well in those wind forecasts is looking at aircraft compression. So while the miles and minutes in trail was looking at the separation of aircraft at a specific altitude, this is looking at a horizontal separation within the airspace. So it can be lost when they're even flying in standard flight procedures if we have enough of a wind shear component to what's happening in the airspace. So if we are getting strong amounts of wind shear, especially in the TRACON areas between the surface and 11 to 15,000 feet, then we could see where we're having flights that are losing altitude and not being able to maintain altitude, and therefore we need to have a larger separation between those planes. So usually planes try to fly with about 1,000 feet separation between them. So maybe one plane's flying at 9,000 feet going one way and they're flying at 8,000 feet going another way. And if they can't maintain that altitude and they start losing their place in the air and due to the wind shear that's involved, then we may have problems and they need to increase that separation, which then again can decrease the amount of capacity in the airspace. So a lot of times compression can occur with a strong low-level jet where we get large changes in the wind speed within a small change of altitude. So in this example here, we're seeing almost 49 knots of compression between the surface and 5,000 feet, which could really have a strong impact on how many planes are allowed to be in that TRACON space and allowed to land at that point in time. Another way that we use the upper air data is to forecast areas of turbulence. So again, we're looking at layers of shear, both directional shear and speed shear, all throughout the atmosphere. Basically, we look at it from anywhere the surface up to 45,000 feet. We're looking for areas of convective lift or convective cloud bases. That can also be a very turbulent airspace for the jets to fly through. We also look for mixing height. That can give us a depth of how deep the atmosphere is going to be mixing in the afternoon, where we can get the turbulent eddies and the turbulence impacting the aircraft, especially in a TRACON area near the terminal. And we also look for detecting adverse winds in the layers aloft. Again, used by the controllers if we're starting to see a lot of wind shear, a lot of adverse headwinds, let's say flying on those arrival routes into O'Hare, then that starts impacting the compression and things that we saw again and can disrupt the regional traffic flow. Other areas we use looking at the upper air data, especially low-level wind shear. So low-level wind shear is detected between the surface and 2,000 feet and can begin with low-level winds in excess of 30 knots. So here was an upper air observation from the Lincoln, Illinois office a couple weeks ago. And you can see that strong detection of shear, both direction and speed. We're looking at around 10 knots at the surface up to around 55 knots at the just off the surface in that lowest 2,000 to 3,000 feet. So we start seeing impacts, especially smaller planes and general aviation, right around plus or minus 10 knots of low-level wind shear. And once we get to plus or minus 20 knots, we start seeing impacts to almost all aircraft and can cause a big deal if we start getting information or low-level wind shear and conditions above that plus or minus 20 knots conditions. Now, one thing to highlight here is in weather service TAFs, we usually start mentioning them above 30 knots. So by the time we get to a low-level wind shear situation in the TAF, it's usually a pretty big impact to the local airports. Some of those impacts then again with low-level wind shear are pretty strong winds depending on the wind direction, can be on runway changes and how the airport is doing a runway configuration. So depending on the runway configuration can impact the arrival and departure rates, lead to compression in those inbound flights like we talked about, which then leads to other disruptions potentially in the en-route traffic in those areas. So here in Indianapolis, we run on two main runways, the 5 and 23 runways for main operations. That allows us about 52 aircraft in and out each hour, or I should just say 52 arrivals. However, if we do end up with a wind direction around like 320 to 340 degrees, we end up having to go to a single runway operation. So that decreases our arrivals and departures by at least half. We end up with a max of only 29 aircraft in. Then if we have other things like low-level wind shear or LIFR conditions or some sort of low ceiling, low visibility precipitation, that can decrease that capacity rate even further. Other ways we use upper air data is to look at icing conditions and forecast icing conditions. We use it to find freezing levels. Looking at cloud bases, their layers, and then also cloud tops are important. We also look for areas of supercooled droplets, which is the main reason we start getting icing in clouds. And then also dealing with precipitation type, usually at the terminals or within those TRACON layers, and then low-level warm layers as well. So icing can be pretty important, especially in the winter. It leads to a lot of aircraft emergencies where we have malfunctions with de-icing equipment, or we have some planes that end up in an area with icing and they're actually not equipped with de-icing equipment. So we get called for aircraft emergencies and have to run to the thing, sometimes could be between seconds and minutes to finding a route to safety for some of those aircraft. Another thing we use the upper air data for is looking for convection forecasts or thunderstorm forecasts, looking at the initiation, the timing of when the storms may erupt. We're also looking at the convective mode or the storm threat for what's kind of expected across the airspace or at a terminal location. We're looking at how much energy is available at the Cape and thunderstorm initiation, the placement and coverage and timing, and especially how intense the thunderstorm may be. So in this is an example of one of our TCF forecasts or a collaborative forecast with the Aviation Weather Center and several other aviation entities. And it basically just gives an idea of coverage and intensity of where thunderstorms can be at different times. And they use this in the traffic route planning. So if they need to say, in this type of situation, plan more of the routes that would be going across Chicago or Indianapolis Center down into Memphis Center, up to the north, up towards Minneapolis Center. So that's another way we use the upper air data. Here is an example, just kind of a gee-whiz look at how the traffic planning routes change. So this is thunderstorms in the area of O'Hare, and you can see every time you see kind of the route switch of traffic that's arriving and departing O'Hare is things that have been put in place by the Traffic Management Unit and the FAA Command Center on where to route the planes. You get an idea of how busy O'Hare is as well. You can see as that thunderstorms, they come in and they try to find any gap in the thunderstorms as possible. So we have a really important forecast challenge of trying to always let them know if there's going to be gaps or if thunderstorms are going to be a solid line. They also want to know how tall the thunderstorms are going to be. The thunderstorms, we get low top convection. We end up thunderstorms maybe topping out at 30 to 35,000 feet. A lot of the traffic can fly over that, especially the en route traffic. But if thunderstorms are, towering up to 50, 60,000 feet or higher, then they have to go around the thunderstorms. And that's where they're trying to find the gaps or any sort of decrease in intensity that they can get the traffic squeezing through a hole of the convection. So that's pretty much what I have, and want to thank you for your time today.
Well, that was some good stuff. We'll have a joint Q&A session for Mindy and Andy coming up at the end of Andy's presentation there. But we did have one question I think is very specific for you, and maybe just because we just came off of upper air, but they were curious. Have you ever had any pilots during briefings talk about encounters with upper air balloons?
I have not. Nope, I have not had any of that information, or at least recently in the last 2 years. Coming up with upper air balloons, just a lot of the icing emergencies, or I'm surprised how many medical emergencies I hear all the time too that are going on in flight. There's emergencies all the time. Makes me a little scared to fly, actually.
All right. Well, thank you for that. And